Hi everyone, this is Dr. J. Nityapriya, Assistant Professor, Department of CS, JJ College of Arts and Science, Autonomous, Pudukkottai. Now we are going to see about spanning trees. Before entering into spanning trees, let us see some information about graphs because only from graphs you are going to derive the concept spanning trees, and the spanning trees are known as the subgraphs of a graph. Okay, so first we see what a graph is. A graph is a non-linear data structure. First of all, what is a non-linear data structure? See, in a data structure there are two types: linear and non-linear. A linear data structure is the one which has all its data in sequence. One by one the data will be arranged. Okay, so that is called as linear data structure. A non-linear data structure is the data items will not be in a sequential manner. It will be arranged in a non-sequential manner. Okay, so in any manner it will be saved without any sequentiality. So that is called non-sequential data structure. For example, we can say a graph is a non-linear data structure, and a tree is a non-linear data structure. A table is a non-linear data structure. So like that we can give examples for non-linear data structures, right? So as far as graphs are concerned, a graph is a non-linear data structure as we saw now, right? So what is a graph? It is a set of vertices and edges. In this slide we see G equals V comma E. V is a set of vertices and E is a set of edges. Okay. So even a graph can contain only one vertex. Only one vertex can be said as a graph. With one vertex we cannot construct an edge, right? So in a graph there may be no edges, but there should be at least one vertex, right? So that is why it is V is a finite non-empty set of vertices. Vertex set will not be empty, but as far as the edge set E is concerned, it can be empty or non-empty, right? So even without an edge, a graph can be constructed. So that is what it means. G equals V comma E, right? Now we see the types of graphs. It has two types, directed and undirected. Right, now we see spanning trees. What is a spanning tree? A spanning tree is a subgraph of a graph. First of all, a spanning tree is a subgraph. Okay, right. When there is something called subgraph, then why we have another concept called spanning tree? See, in a subgraph, subgraph will be a portion of the graph. Maybe in a graph, if it contains 4 vertices and 4 edges, the subgraph may be containing 3 vertices and 2 edges, right? So some portions may be missing in a subgraph, but in spanning tree all the vertices should be present in that particular subgraph. So that subgraph is called as a spanning tree. So we can see the example. It is a subgraph which has all the vertices of the graph G, and the second condition is it should not form a cycle. There should not be any cycle in a spanning tree, right? So I hope you understand. A spanning tree is first of all a subgraph of a graph. Secondly, it should contain all the vertices of the given graph, and thirdly, it should not form a cycle, right? So see the graph G. It has 4 vertices and 6 edges, right? And see the spanning trees on the right side. We can form 3 spanning trees for the given graph G, right? So I hope you understand the concept of spanning trees. Now we see how about the minimum cost spanning tree is formed, right? First of all, for forming a spanning tree we can follow 2 methods. Okay, generally we will follow 2 methods: picking up the edges and constructing the spanning tree, and picking up the vertices and constructing a spanning tree. Both the ways we can construct a spanning tree out of the given graph, right? Okay, so we have 2 algorithms like Kruskal and Prim, right? Now we are going to see Kruskal algorithm. We are not going to see Prim's algorithm. Kruskal algorithm is it is picking up the edges, right? So Kruskal algorithm, it finds a subset of edges that form a tree. That spanning tree, of course, it includes every vertex. Okay. So if there are n vertices in the spanning tree, the number of edges would be obviously n minus 1, right? So if there are 4 vertices, there will be 3 edges. If there are 5 vertices, there will be 4 edges, and so on. Now here we have a graph which is on the left side, right? So this is the graph we took today. Now from this graph we are going to form a spanning tree. See, the spanning tree is, first of all, in Kruskal algorithm, the thing we are going to see now, we are seeing now is Kruskal algorithm, right? Kruskal algorithm constructs a spanning tree by picking up the edges, right? I'll go to the algorithm later. In this graph, the first edge which will be taken is 2, 3, right? The edge that connects the vertices 2 and 3. So what is the weight of the edge? It is 5. Out of all the edges present in this graph, that is the minimal cost edge. So that would be picked up first. So 2, 3 would be the first edge. What would be this next one, second one? There is an edge 6, and that is in between 2 and 4 vertices, right? So first 2, 3, then 2, 4. Okay, right. The next edge would be 10. See, 10, the edge of cost 10, which connects 3 and 4. Can we pick that edge? Can we pick that edge? No, because the constraint of the spanning tree says we should not form a cycle. When we have an edge 2, 3 and 2, 4, 3, 4 cannot be picked up, because when we pick 3, 4, it will form a cycle, right? So we just drop 3, 4. Okay, right. Now go to the next edge, which is of course 11, that connects 2 and 6. Okay, so that is the third edge. And nextly it is 14. 14, the edge of cost 14, that connects 4 and 6. Can that be taken? No. When that is picked up, that will also form a cycle, right? So we just drop it. Now we have picked up only 3 edges of cost 5, 6 and 11. Okay. The next edge which would be taken would be 16. 16, that connects 1 and 2. And eventually we take the edge which of cost 18, that connects 4 and 5. Okay. So now at this status, all the vertices have been included in the subgraph. So at this juncture we can stop. Okay. So otherwise we can consider the other edges also. For example, 21, that connects 1 and 6. But 1 and 6 vertices, they are already there in the spanning tree. So we take the edge 21. Okay. Consider the edge 19. See, already the vertices that is connected by the edge 19, 1 and 5 are already there in the spanning tree. So we need not take the edge 19. Consider the edge 33. How about that? That connects 5 and 6. So that vertices are also there in the spanning tree already. So we just drop that edge also. So the final spanning tree we construct out of the given graph is this, that is present on the right side. I hope you understand. Now we see the algorithm for Kruskal. Right, T equals pi. T is called as the subgraph. In other words, it can be said as the spanning tree. Okay, T is the set of edges picked for constructing the spanning tree. At present, initially we haven't yet started constructing the spanning tree, so T remains pi, which is an empty set. Okay, so while T contains fewer than n minus 1 edges, what about this constraint? When a spanning tree is formed with n vertices, obviously the number of edges would be n minus 1, that we saw in the previous slide. Okay, in early slides we can come to know that when there are n vertices in a graph, the spanning tree should contain only n minus 1 edges. Okay, because that would be containing all the n vertices of the graph, and that would be obviously containing n minus 1, right? N minus 1 edges, right? So the constraint here is, while T, the number of edges in the spanning tree, while T contains fewer than n minus 1 edges, only at this constraint the loop can start, and E is not equal to pi. Okay, E, what about E? E is the number of edges in the given graph. Okay, right. E should not be empty. there should be at least one edge in the graph, because Kruskal algorithm leads us to pick up edges. Okay, so the number of edges should not be empty there. So that is the next constraint. Okay, right. So when T contains fewer than n minus 1 edges and E is not equal to pi 2, right. Choose an edge v comma w. That is an edge we are picking up now, right. V comma w. V and W are the vertices that connect, that is connected by the edge that we are considering now, and the edge is E, capital E, okay, of lowest cost, because we are constructing minimum cost spanning tree. We are taking an edge of lowest cost. Obviously we'll begin the process by taking the edges with lowest cost. We'll start with 5, 6, 10, 11, 14 and so on. We cannot straight away pick up an edge with the cost 14 when 5 is there. Okay, we cannot do that, because that is a minimum cost spanning tree. We should pick edge with minimum cost, right. We have to start with an edge with lowest cost. That is what it means, right. So when we take the edge from the graph, it should delete that edge from E. So what is E? E is the number of edges in the given graph. When particular edge from E is taken out for spanning tree, that has to be deleted from E. That should not be considered again. Okay. So V comma W has to be deleted from E. Right. So the second thing we are going to do is checking if the particular edge VW is forming a cycle. Okay. It should not create a cycle. When it creates a cycle, that should be dropped. Okay, so that is this. If V comma W does not create a cycle in T, then add V comma W to T. What is capital T? T is the number of edges taken, or T is the number of edges of the spanning tree. Okay, right. So, or else discard V comma W, right. If it creates a cycle, okay, it has to be discarded. That should not be considered, but it has to be deleted from E. It should not be added on T if it forms a cycle, right. So why we are deleting is from E? We cannot consider it again. Okay, right. Again and again we cannot see. We need not see the same edge. We need not work on the same edge again and again. That is why we are deleting V comma W from E, and we are deleting it from T. Discarding it from T. I hope you understand, right. So with this, we are considering the edges again and again and working on it, right. Okay, so that is how we form a cycle. For when we take each and every edge, that will be checked against forming a cycle, that will be checked against if it has a lowest cost, right. So both the conditions are checked, then both the conditions are okay, that will be added in T, right. So finally, for the given graph with n vertices, the spanning tree that we would have constructed would be having n minus 1 edges with n vertices. Okay, so that is about minimum cost spanning tree, right. I hope you understand this video, and thanks for watching.